Hello everyone, my name is James Davis and I've decided to do my algorithm presentation on the closest pair problem, which is designed to find the distance between the closest pair of points in space. Suppose you have various random points just out there in space, and suppose you want to find the distance between the two closest points, which are these two, as you can look and see, but you can't always do that with the computer. There are two different methods of doing so that I looked at. I looked at a brute force method and a recursive method, both of which I will explain in due time. But first, who cares about points in space? Well, gamers do, because when I'm gliding around Arkham City looking for bad guys to pummel or Riddler trophies to find, which is a shameless plug, I want to know what the shortest distance between the nearest important thing, point A, and me, point B, for Batman, is. But computer science was not developed solely for gaming reasons, and because of that, I'll throw in a real-world application to this problem: air traffic control. Planes flying around in the air that fly too close to each other tends to crash, and that's a bad thing. So you want to know what the shortest distance between two planes flying around the air is, and if they get too close, you want to warn them. Both of those are dynamic examples. Another example would be emergency personnel. If my house is on fire, all police, fire, and EMS will be sent to my burning house, and I would like that to happen as quickly as possible, so I hope they're using the recursive formula. Police, which are out and moving about, would be dynamic examples, whereas firefighters and EMS are usually stationed at the fire station, and that would be a static example. So let's talk about these two methods. First of all, we'll talk about the brute force method. Here's all of our points in space, and here is a graphical representation of these points in space. So with the brute force method, you will test point A, not point A and point A, but point A and point B. The distance between those is D. Point A and point C, the distance between those, if it's shorter than B and A, then it's D. Otherwise, we'll skip that. And so on. And as you can see, that's big O of n squared, and you can see why that's big O of n squared. Made some modifications to the brute force method. One of the modifications I made is, instead of testing between A and B and then coming back later and testing between B and A, I just eliminated this whole second half of the graph here. And these two, of course, and so on. Another thing that I did was I looked at the distance, we'll say from A to B, we'll start there, call that D. Then from A to C, if delta x, change in the x coordinates, is less than D, then if delta y is less than D, then we'll go ahead and find that distance formula. It didn't shave a ton of time off, but it did shave a considerable amount. You don't have to call that distance formula as many times, which, helps. I realized that I could make these two modifications after I worked on the recursive formula for a little while, but before I was successful at it, I struggled with the recursive formula for a little bit, and then these are two modifications that I thought of. Well, the first one I thought of to begin with, but the delta x, delta y, I thought of after I was working on the recursive one. So the recursive method, we'll show that one here. Alright, and we'll make a couple modifications to our points in space here. I realize for explanation purposes it'll make a lot more sense to have these points right here. Okay, so with the recursive method, we're going to sort them all by x coordinate. We're going to go to the very middle one, and we're going to draw a line down here, imaginary line. Then we're going to find the shortest distance between all the points on the left side, and then we're going to find the shortest distance between all the points on the right side. So, and we'll do that recursively. So we'll come over here, we'll draw our little imaginary line there. We'll see that this is the distance right here. these distances. This is the shortest distance. I'll show this next part. You would do that on this step as well, but it'll make more sense to show it over here. We'll find this shortest distance right here, and then over here there's no, I guess this is the shortest distance. What we're going to do is we're going to take this distance right here, and we're going to go from that middle point out d units, whatever that d is, the shortest distance between the left side and the right side. Then we're going to measure everything that's within this area right here. This lies right on there, so for explanation purposes, we'll measure that. These you can see is a little bit further apart than this distance right over here, and so we end up with this distance over here. But it's important to test in between here because sometimes the distance could be there. Now let's look at a little bit of code here. I'm going to go ahead and start running this for testing purposes so that we can see what. Well, that's not the one I want to run. So that we can see some of these numbers get. It takes a long time to add. 20,000 points adding to an array doesn't take as much time, but whenever we get to adding 100,000 points, that takes a while. So I'm starting the testing now, and then we'll go back and look at some of the numbers here as we get further along. For right now, I'll go down here and I'll kind of walk through this recursive method. What we're going to do is if we're going to take this subarray, and if that's just one point, we're going to return infinity, which is just the maximum amount for a double, in this case, a practical infinity instead of a literal infinity. If there's 2 points, then we're going to find the distance between them, and if there's more than 2 points, then we're going to pick the middle point. We're going to find the distance between everything on the left side, distance between everything on the right side, find the minimum between those two distances. And then this little bit right here, what we're going to do is we're going to do this part over here. We're going to find how far out we need to go to the left and to the right, and then we're just going to test every point in between there, just our brute force method, modified brute force method. Then we're going to return the shortest distance, and we will get shortest distance between the points. So let's come back here and look at some of our testing. At 10,000 points, you can already see there's a huge difference between the recursive method and the brute force method. The brute force methods, you can see that the modified brute force method cut the time in half, but 200 milliseconds compared to even 13 is considerably more. For some reason, most of the time, whenever I would run it, the recursive method the second time around would always go faster. I don't know the reasoning for that. But you can see at 30,000 points, it's already 4 seconds compared to 10 milliseconds. At 50,000 points, then we have still about 15. And as we get closer, as we get more and more points, you can see that it doesn't quite cut it in half. But 15 milliseconds or 15 seconds cuts off 4 seconds by doing the modified brute force method. But this distance measured by the recursive method is 1,000 times quicker, I would say. So hopefully you would think that airplanes flying around, air traffic controllers would want to use this recursive method, because as we might see if we don't run out of time here, I mean the distance between 120,000 points, well, I didn't even measure the distance by brute force that way, because the distance between 70,000 points, little over half as many, still took 36 seconds to do. And you see the modified brute force method at that many points doesn't shave a whole lot of time off. A couple of problems I ran into, I'll tell you, whenever I was doing this, while this last one is running, is the Java, whenever it figures my distance formula, it took the distance between the x-coordinates squared and the distance between the y-coordinates squared, adds them together and takes the square root, like the distance formula does. real quick here, you can see 220,000 points. The reason it's a little less is because I told it not to include duplicate points. You can see it did that in less time than it did 10,000 points by the brute force method, the modified brute force method. So recursive method just kicks butt all the way. Like I was going to say real quick before I close, a couple of problems I ran into, so you guys might want to watch out for this if you're having some trouble here. I did the limits that I was using, and then I started pretty small with like 5 points at about the maximum, half the maximum, half of the value of a maximum integer and a minimum integer that you can have in Java. Well, I got a distance of 46,000 points, or 46,000 units. Well, if you square that, 46,000 units, as we will see here, 46, the exact number was 847 squared. You can see that's 2,194,641,000. But whenever Java does it, one thing we're learning in the, or we've learned in the assembly language class is 2's complement. And it just kind of dawned on me whenever I was doing this that you see I do 46,847 squared, print out that, and it comes up with negative 2,100,000,000. Because of the 2's complement there, that first digit was a 1. Yeah, I spent a lot of time debugging that before I finally realized that. So anyways, that's my algorithm presentation, shortest distance between 2 points in space. Yeah, thank you very much, and have a great day.